Look at this split-screen code execution. On the left, we set x to 5, make y equal to x, and then update y to 10. The original x remains exactly as it was. But on the right, we do the same thing with a list. We create list A, assign it to list B, and append a 2 to list B. Instead of acting independently, the update modifies the original source list. The difference comes down to how Python treats memory. Integers are immutable data types. When you change an integer, Python doesn't edit the existing data. It ignores the old value and creates a brand new one in memory. Lists are mutable, meaning you can change them in place. When you assign one list variable to another, you aren't making a copy of the data. Both variables act as separate links pointing to a single shared location in memory. We can see this by running Python's built-in ID function. This tool reveals the raw memory address of any variable. When we test both list A and list B, Python returns the exact same memory address integer for both. They are two names for one object. Distinguishing between these memory links allows you to ensure that updating one variable doesn't accidentally overwrite data stored in another. To create a duplicate that you can safely modify, use the slice operator. By assigning a variable to a list with open slice brackets, we force Python to create a true, independent copy in memory. When we run the ID function now, we get two separate addresses. This memory management remains a factor as data structures scale. When a list contains lists inside of other lists, the linear data fractures and stacks, creating a two-dimensional structure. It is easy to misread this grid like a standard math graph, checking horizontal x-coordinates first and vertical y-coordinates second. However, Python reads 2D lists by rows and columns. We first move down to find the correct row, and then across to find the column. We isolate a specific data point using double bracket syntax. The first bracket tells Python which row list to drop into, and the second bracket tells it which column index to pull from that row. Internalizing this down then across order allows you to predict exactly which coordinate your code is targeting at any given moment. Manually targeting one cell works for small tasks, but to process an entire dataset, we need a way to automate the movement across every row and column. We solve this with nested loops. The first layer is the outer loop, utilizing range, len, grid. This loop is responsible for traveling downward, row by row. Think of it like the roller of a vintage typewriter clicking down the page. The inner loop operates entirely inside the current row. It sweeps left to right across the columns, checking each individual cell in sequence, just like a typewriter carriage moving across a single line. By formatting the inner loop as len grid r, the code calculates the exact length of the current row. This ensures the loop successfully sweeps every item, even if the data matrix is jagged and not a perfect square. Pause the video here. Using these mechanics, write a function that searches a 2D matrix for a specific target value and returns its exact row and column coordinate. This structure creates a predictable path, ensuring no data point is skipped during a search. Here is the logic for that search. We use our outer loop to handle the rows and our inner loop for the columns. The if statement nested in the center evaluates the exact coordinate to see if it matches our target. Notice the execution flow. The inner loop must complete its entire left-to-right sweep of the columns before the outer loop moves down to the next row. It is an exhaustive, cell-by-cell search. As you write larger programs, keep these 3 rules in mind. First, use slicing to physically duplicate mutable data and protect your source lists. Second, remember the layout of the matrix. Mapping coordinates requires moving down the rows first, then across the columns. Finally, when navigating grids, the outer loop measures the total height of the grid, while the inner loop measures the length of the specific row it is on. Understanding how Python manages memory addresses and how nested loops traverse dynamic rows gives you precise control over how your program interacts with multidimensional data.